My name is Bryan Kelly, and I'm a firmware engineering manager at Microsoft. And I'm here today to talk about data center server agnostic power management. And before I do, I want to maybe give a little bit of a backdrop into the architecture, and then get into the agnostic nature of the power management. So I want to give you an overview first, so when I start talking about various components, you understand where I'm going with it. So this is the Project Olympus system overview. This was contributed into Open Compute in 2017. We have the rack architecture and the PMDU, which is our power management distribution unit. This has a management module, which is a little SoC with some co-processors that perform some of the power monitoring in the rack. We've got the server that goes into the rack and blind mates with that PMDU, so there's no cabling. So you'll see that the power supply, or the PSU on the server, is I can get a little pointer here for maybe first. This PSU here is blind mate into this power management distribution unit. We call it normally this would be called a PDU, a power distribution unit. It's called power management because it also carries some signals that are important to our power control to turn off individual sockets or outlets on the PDU, and also some alert signals for power events, so we can react to them in a very, very timely manner. This is the overview. We've open sourced the firmware. We've got OpenEDK, OpenBMC, and the rack manager firmware is also open sourced, along with the manufacturing collateral for the components in the rack itself, and the PMDU. You see here we've got servers, we've got storage units, and some other devices. I'm going to try to skip through this to get to the meat of the presentation, but I want to give you an overview of the architecture. So the power management distribution unit, as I mentioned, we've got the power sockets all coming out of the PDU. It's got a universal plug connector for allowing us to go into different data centers and regions without changing out the PDU and the rack. We've got the hot plug rack management module. This is what's doing the power metering. It's got a series of ADCs that connect to CTs that go around the three phases inside in the PMDU. We've also got this device down here, which we're going to talk about in a little bit, which is standalone rack manager. If you have infrastructure that doesn't have this PDU, but it's got a traditional PDU in the rack, this standalone rack manager can bring some of that same functionality to a non-Olympus rack. It also serves as a row and colo manager, which we'll talk about in a little bit. The universal PMDU, some things about it is it's got dual feed, so you see the two cables coming into it. Interestingly, the different connectors throughout the world, they just plug in. Actually, they connect in on the power outlet. We have different leads that will connect in here, so you don't have to change out the full PDU, which is, if you've worked in data centers and you've had racks go to different locations and be reassigned on short notice, taking out a PDU is pretty painful, and recabling all of that infrastructure. So this enables rapid deployment at scale. When stuff gets reassigned to different locations, it's just a cable change here, and there's a quick release connector for that cable. The PDU carries three phases inside in it, so we deliver three-phase power to the racks, and the infrastructure is phase balanced within the PDU, so we don't have to worry about phase balancing and cabling to have the device, to have the IT load phase balanced. Power supply that I talked about earlier is a three-phase power supply, but it's made up of three individual single-phase power supplies that deliver 340 watts. And why this is relevant in a power capping talk is one of our scenarios for power throttling or power control is when we get power failures. So the three individual single-phase power supplies that make up this single unit of a three-phase power supply, if one of those units inside that power supply fails, then our total is 680 watts. So if the IT load, or if that server is running below 380 watts, then there's no need to power throttle. If you get a double fault or double failure where for some reason the second PSU was to fail, or you were to lose a phase while you were on two power supplies, you can have a double fault, and you would go to 340 watts. If the server is still below 340 watts, then there's no power capping that would occur. If the server is above 340 watts, its power will be reduced to 340 watts through a power capping mechanism. So to recap some of the flow, we have PMDU, which fans out some GPIO logic from the rack manager and goes into all the servers through that blind mate connector. Our servers get configured with a power policy based on their assignment. So critical servers will have a power policy that is full power, no throttling. Servers that run workloads that we would consider internal or sacrificial, we call it evictable, those workloads will get a power policy that when there's a power event, they're the first to get reduced in power. Rack manager performs the power metering across all three phases. It gets assigned a rack limit. When that rack, or if that rack exceeds that limit, those servers will activate their power policy. The signaling mechanism will be that logic level signal through the GPIO that's fanned out through the PMDU. There's also the option on the rack manager for some auxiliary inputs. So auxiliary inputs can come in to take data center events, and we'll get to that in a little bit. So the baseboard and the logic on the baseboard, this diagram looks maybe complex, but I'll give you an overview of it. So I talked about the PSU earlier and the PSU events. So we had those three individual single-phase power supplies. We could lose one. If we lost a second one, then we'd have to reduce power. So we configured a PSU firmware on a power overcurrent event. It will drive out an alert, and that alert in our baseboard management controller, we have control of these gates that will allow that alert to propagate through and result in the power capping event. Similarly, we have another signal that comes into the server, and that's from that rack manager, and we call it rack manager throttle. So if there's a power event at the rack, it'll drive in a signal, and if the policy which resides in the BMC firmware, if that's enabled to allow that event to propagate through, it will result in a power capping event. So on Intel architecture, they have their management controller inside in the PCH that performs power management, power control. You can set a power limit. It will go and pull the hot swap controller on the server, get what wattage the server is running at, and then keep the server below that limit by changing the CPU frequency. The signaling goes into on x86. That signaling will go into their management engine. can also propagate to the CPUs. One of the reasons it will propagate to the CPUs is if it's an event that requires very low latency. We don't want to rely on just software for that event. So we have the ability or the option to go in and drive proc-hot. And what proc-hot will do is it will instantly reduce the frequency of the CPUs, the power of the CPUs, and then we'll come in through the management engine. We'll set a power limit, and then remove the proc-hot, and the server will run at that power limit. So what you have is this power value running real high, this instantaneous drop, and then immediately a bounce back to the power limit. When we run without that instant drop, what happens if you put a power policy on the EME, or you try to implement some RAPL-based power control at the CPUs, is you see the power come down gradually, and that slope, that pull down in power can vary. That time window can vary. So you can either have instantaneous power drop depending on the severity of the event, or you can have a gradual power decay down to your power limit. So that was good for Intel servers, but where they have that management engine that's performing some of that power polling. So if I come back to it, this Intel management engine is going out and polling the hot swap controller. What about servers that don't have that? So our ARM64 architecture or AMD that don't have that proprietary management controller in their chipset. And chipset-less architectures. What did they do? So the solution is actually very similar, but much of that functionality that's performed in the ME just gets routed to the baseboard management controller itself. And this has a coprocessor, and in the BMC that we have on our Olympus motherboards, this has a coal-fire coprocessor that can perform the same functionality. So the coprocessor goes and pulls the hot swap controller for the power of the server going into the motherboard, and it can set RAPL policies on the CPUs or power policies on the CPUs, and can adjust what the CPU wattage is based on the server wattage as a whole. You still get those same signals, those same alert signals for those events that require rapid response. So putting the flow together, we have a hardware interrupt that can come based on a rack power limit that can go into the server and cause it to instantly reduce its power and run at a defined power limit. We have event-based remediation, and we have a series of events that we collect from the telemetry and events that we collect from the power meter in the PMDU. So it all leads us to moving away from having static power policies on servers and having servers run at a set power limit. Like the server, if you're running servers at a set power limit, they're going to be they're not running to their full performance. You want to have them ungoverned or unrestricted. Let them run as high as they like. Once they end a rack or at the row level, cumulatively they don't exceed those hard power limits of the infrastructure. So to give an example of that, we have what we call dynamic rack level power control, where some servers in the rack will receive power policies. Those will be the workloads that we have that we could sacrifice, or those evictable workloads. The rack manager will be set with a rack limit, and it will monitor the power of the rack. So as servers run hot, that power will increase as we increase load on some servers, and this will bounce around all the time typically. And then as some servers run even hotter, we'll bring that power right up. And then you're getting close to a tripping point for the rack, as if you were to go into the tripping point. In this case, if we reach that rack limit, the rack manager will trigger an alert, and servers that have defined policies will go back down to their operating limit. Other servers will be allowed to run hot. That, in essence, is how the system works. So critical workloads will be allowed to continue to run hot. Some workloads will be throttled, and it really varies depending on the application that's running on the node. So then that's great for dynamic rack level power monitoring. But if we want to take it maybe a step further, if the rack is not the limit, the bottleneck, if the rack infrastructure can run higher, that limit might go to a row of racks, where you have a breaker at the row that is the bottleneck for how heavy you can load each rack. And if you want to push that envelope, well, we have the device to do it. So I mentioned earlier, there was another module in the Olympus architecture called a row manager. And this serves as multiple functions. It's the same module that goes into that PMDU, and it's the same firmware. It's just a different role that it takes, and then it plugs into a different device that we call the standalone rack manager, row manager, and it also serves as a colo manager. It looks a little bit like a switch because it has a bunch of RJ45 ports on the front, but those are not network ports. They carry signals to each of the rack managers, and those signals contain power control for power cycling a rack manager, and they also contain some bootstrap for changing boot orders of rack managers, and then they contain a rack level throttle. So from a row or from a row event that's running on this device, we can trigger racks to alert or to drive their alert, and then those blades will receive that alert into their baseboard management controller. And if the policy on the blade informs it to reduce its power, that's the action that it will take. So the architecture scales out. And then, of course, once you have rack level power control, and that might be set at one limit, and then you'll have a row level power control that might be oversubscribed or more than what the row budget allows. Once you have rows that are capable of running beyond their budget, then the next level in your power distribution becomes the bottleneck or the next limit, which is the row. So at that stage, you have these redundant colo managers, which can also monitor devices at the colo level, which might be your UPS or some input power from a input source into the colo, or input breaker at the colo. And that can distribute events out to these row level managers, which in turn will redistribute the event to these rack managers. And then overarching across all of this, of course, you're making sure that before you get these events, you're reassigning workloads accordingly to where you have capacity. For more information on Project Olympus and that infrastructure, you can find it at the following links. We also have a rack downstairs where you can see that rack manager, that power distribution unit, the colo manager, and how that all fits together. So with that, I'll open it up for any questions that anybody has. Shoot.
Yeah,
Oh, we get a mic.
trying to get things going here. Which project, so the firmware, is there a specific project within Open Compute that's getting submitted or worked on?
Yeah, so there's, for the firmware, there's a couple of components. There's the Open UEFI, which I think there was a talk earlier today, and there's a demonstration on its performance in terms of boot down in our booth. But there's the Open UEFI, which is here. There's Rack Manager, which is that management module that goes into the PMDU, and there's Open BMC. I didn't put the Open BMC on here. There's also Open BMC that runs on all of the infrastructure that we have.
Great, thanks.
Right. So all other firmware is available and a manufacturing collateral. Any other questions? Sean?
So how do you configure these rack manager, BMC kind of processors?
Yeah. So the rack manager, the BMC and the rack manager are configured by our fabric. So there's firmware that's going to run in the baseboard management controller, and that firmware allows for a policy to be assigned to the blade. And what the policy tells it is when it receives this alert from the rack manager or from its PSU failure, what actions it should take. So our fabric software will talk to the BMC and tell it, hey, when you receive this alert signal, reduce your power to 340 watts, reduce your power to 400 watts, do nothing, just ignore it. And it makes the fabric makes those decisions based on the workload it's assigned to the server. And in the rack manager, that is pre-installed with firmware also and gets updated through the fabric. And it gets assigned a policy that says, hey, this rack you're being deployed into is a 20 kilowatt rack. Don't let the infrastructure exceed 20 kilowatts. Or in the event of the row limit, it will divide up what the row limit is and say, don't let your racks cumulatively exceed these, and he'll assign that policy to the row manager. So everything is configurably dynamic.
My question was the fabric. Where's the fabric coming in for the row manager? It didn't show up in these block diagrams.
Bryan, tell them about redfish commands.
The interface, yeah. So
How can they do it
if they don't have it? I see. So the interface into the rack manager and into the BMCs, of course, is redfish. So you have some web interface, some JSON web interface that you want to configure these things and set those policies. There's APIs, and there's a specification published on what those APIs are and what they look like, and that's part of that. If I skip back down to it, that link for the Project Olympus collateral, in there's not only the schematics and board files for the infrastructure, but there's also specifications for software APIs that you would call to go and configure these policies and to read back the power consumption and to monitor the telemetry. And that's all done through redfish. And for us, our fabric will go and call those redfish APIs and do that configuration for us.
Which type of the power policy do you use? Is it a P state, T state, mixed, or power budget? And why it is so?
Yeah, it's really a combination. So it's kind of cumulative, and it's based on how low you actually need to take it. You obviously can't go below P min without powering the device off. Which, depending on how sacrificial the device is and what type of workload it is, power control is an option in there in the policy. But we assign a wattage power limit, and then in the firmware, it will interact with the device to get it as low as it needs to get to achieve that platform level power budget. So that will include reducing the frequency and transitioning P states and T states. So, any more questions? Clear as mud? All right. Thanks a lot, guys.